Imagine looking down at Earth from very far away. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From that great distance, our planet looks like a small blue marble, wrapped in swirling white clouds, floating in a sea of black nothing. Most of what you see is water. The oceans cover about 70% of Earth's surface. They shimmer and shift, catching light from the sun, vast and deep and ancient. And somewhere nearby, a little smaller, a little dimmer, hangs the moon. It looks quiet up there, still, just a pale gray rock drifting in silence. But the moon is doing something remarkable. It is pulling on every single drop of water in every ocean on Earth, right now, without stopping, without rest. That pull is gentle. It is invisible. You cannot feel it standing on a beach, but the ocean feels it. The ocean responds to it every single day in one of the most steady and reliable rhythms our planet has ever known. We call that rhythm the tide. The moon is about 239,000 miles from Earth on average. That is a staggering distance. If you could drive a car at highway speed without stopping, it would take you more than 5 months to get there. And yet, across all that empty space, the moon's gravity reaches down and moves the ocean. Gravity is the force that pulls objects toward each other. Every object in the universe has it. The bigger the object, the stronger the pull. The moon is not small. It is about 1/4 the size of Earth. That is large enough to matter, large enough to move water. The moon's gravity does not pull the whole ocean equally. It pulls hardest on the part of Earth closest to it. That side of the ocean gets tugged outward, just slightly, forming a gentle bulge of water. On the opposite side of Earth, the water there gets left behind a little, forming another bulge. Two bulges on opposite sides of the planet at the same time. As Earth spins, different coastlines pass through those bulges. When your beach is under a bulge, the water rises. That is high tide. When your beach is between the bulges, the water falls back. That is low tide. It is one of the oldest dances in our solar system. What makes this so wonderful is how old it is. The moon has been pulling at Earth's oceans for billions of years. for humans to watch the waves come in and go out, long before there were animals on land, long before there were fish in the sea. The tide was already rising and falling. The same quiet rhythm over and over for billions of years. Scientists estimate the moon formed about 4.5 billion years ago, likely from a collision between early Earth and another large rocky body. From nearly the very beginning, it has been pulling at the water below. The ocean has never once ignored it. Stand on any beach at the right moment, and you can feel the weight of that history. Watch the water creep up the sand, slow and steady, leaving a dark, wet line behind it. That water is responding to something 239,000 miles away. The moon does not touch the ocean. It never has. It simply pulls from a distance, and the ocean leans toward it, the way a flower leans toward light. There is something deeply calming about that. Something that makes the universe feel less random and more like a place where things respond to each other. The moon and the ocean are in a constant, quiet conversation. Scientists who study tides are called physical oceanographers. They have mapped the tides in every ocean, in every bay, along every coastline on Earth. They have built models that can predict to the minute when the tide will rise and fall at any point on the planet. And at the heart of every single one of those predictions is the moon. That pale gray rock, drifting in silence, doing its slow and steady work. Tonight, while you rest, the tide is moving somewhere. A beach in Iceland is watching the water pull back over dark stones. A mangrove forest in Brazil is slowly flooding as the ocean rises through its roots. A harbor in Japan is deepening as the sea climbs its old wooden docks. All of it connected, all of it driven by that one quiet pull from above. The moon never stops, and neither does the sea. So what exactly is a tide? At its simplest, a tide is the rise and fall of the ocean's surface. It happens because the moon pulls on the earth, and the ocean, being liquid, responds to that pull. The land responds too, but rock is stiff and hard. Water moves freely. So the ocean is the part we notice most. The moon sits about 239,000 miles away from Earth. That sounds impossibly far, but think of it this way. If you could drive a car straight up into the sky at highway speed, you would reach the moon in about 5.5 months. It is far, but not unreachably far. In the scale of the solar system, the moon is practically next door. And that closeness is exactly why it has such a strong grip on our oceans. The moon is not a small object. Its diameter, the distance from one side to the other, is about 2,159 miles. That is roughly the width of the entire United States from the East Coast to just past Denver, Colorado. It weighs about 81 times less than Earth, which makes it much lighter. But it still has real, measurable gravity. Gravity is the invisible force that pulls objects toward each other. Every object with mass has it. You have it. The moon has a great deal of it. Isaac Newton was the first person to describe, in precise mathematical terms, how gravity works between two objects. He showed that every object in the universe pulls on every other object. The strength of that pull depends on two things: how massive the objects are and how far apart they sit. The moon is massive enough and close enough that its pull on Earth is not just a theory. It is something the ocean feels every single hour of every single day. Here is where tides begin. The moon's gravity does not pull on all parts of Earth equally. The side of Earth facing the moon is closer to it, so it feels a stronger pull. The side of Earth facing away from the moon is farther, so it feels a weaker pull. This difference in pull across the width of our planet is called the tidal force. That word, tidal force, simply means the stretching effect caused by uneven gravity. It is the same reason a rubber band stretches when you pull harder on one end than the other. Earth's diameter is about 7,918 miles. That is a significant distance. And across that distance, the moon's gravitational pull is noticeably stronger on the near side than on the far side. The ocean on the near side gets pulled slightly toward the moon. It bulges outward just a little. Scientists call this a tidal bulge. It is a gentle swelling of the ocean's surface, maybe a foot or two higher than the surrounding water in the open sea. Out in the deep ocean, you would never feel it passing beneath a boat. But when that swelling reaches shallow coastal water. It piles up and becomes the high tide we can see and walk through. The ocean on the far side of Earth also bulges outward, but for a slightly different reason. On that far side, the moon's pull is weaker than the pull felt at Earth's center, so the water there effectively gets left behind as Earth is pulled slightly toward the moon. It bulges away from the moon in the opposite direction. This is why, at any given moment, there are two bulges in the ocean at once, one facing the moon and one facing away. Two swellings on opposite sides of the planet, always present, always moving. As Earth rotates, spinning on its axis once every 24 hours, different parts of the ocean pass through these two bulges. When your coastline rotates into a bulge, the water rises. That is high tide. When your coastline rotates away from a bulge, the water falls back. That is low tide. The whole system is elegant in its simplicity. The moon holds still, roughly speaking. The earth spins beneath it, and the ocean sloshes gently as each coastline passes through those two quiet swellings in turn. This is the engine behind every tide on Earth. Not a storm, not a current, not the wind. Just the steady, invisible pull of a gray rock 239,000 miles away, and the slow spin of our own planet beneath it. Two simple motions working together, producing something the ocean has done without pause for billions of years. The tide rises, the tide falls, and the reason, when you strip everything else away, is beautifully simple. The shape of those two bulges is worth slowing down to understand, because the ocean does not simply pile up in a neat, round heap on the side facing the moon. The real shape is stranger than that, and the reason why tells us something deep about how gravity and motion work together. Picture the Earth floating in space. The moon sits off to one side, pulling on everything it can reach. But here is the key. It does not pull on everything equally. The side of Earth closest to the moon feels a stronger pull. The side farthest from the moon feels a weaker pull. Gravity works that way. The closer you are to something, the harder it pulls on you. This difference in pull across the width of the Earth is called the tidal force. It is not simply gravity. It is the difference in gravity from one side of the planet to the other. That difference is what stretches the ocean into its two-bulge shape. On the near side, the water gets pulled toward the moon more than the solid earth beneath it does. So the water rises up, reaching slightly toward the moon. On the far side, the solid earth gets pulled toward the moon more than the water on that far edge does. So that water gets left behind, rising up in the opposite direction. The result is an ocean that looks very slightly like an egg, stretched gently along the line pointing toward the moon. Both ends a little fuller, both sides a little flatter. The stretching is not dramatic. The average height difference between a tidal bulge and the surrounding ocean out in the open sea is only about 1 to 2 feet. The ocean is so vast and so deep that this gentle swelling is almost invisible from above, but it is real. Scientists can measure it precisely from satellites. What makes this even more interesting is that the solid earth bulges too. Rock is not perfectly rigid. Under the tidal force, the ground beneath your feet actually rises and falls slightly, just like the ocean does. This is called the earth tide, and it moves the ground by as much as 12 inches in some places. You cannot feel it. You cannot see it. But instruments sensitive enough to detect the faint trembling of distant earthquakes can measure it clearly. The whole planet breathes in and out, very gently, twice a day. The ocean's bulge also does not sit perfectly still. It would if Earth were covered entirely in water with no land in the way. But continents interrupt the flow. Ocean basins have their own shapes, their own depths, their own rhythms. The water sloshes around inside these basins, the way water sloshes in a bowl when you tilt it. This means the tidal bulge gets shifted, delayed, and reshaped as it moves around the globe. In some places, the tide arrives hours later than a simple model would predict. In others, the shape of the coastline focuses the water and makes the tide much taller than it would be in open ocean. The ocean is not a smooth, featureless sphere. It is a complicated, irregular world of basins and ridges and shelves. And the tidal bulge has to negotiate all of it every single day without stopping. There is something else worth knowing about the bulge. does not point exactly at the moon. Because Earth is spinning, the bulge gets carried slightly ahead of the moon's position. Imagine dragging a wet cloth across a table. The cloth bunches up just ahead of your hand, not directly beneath it. Earth's rotation does something similar to the tidal bulge. The ocean's highest point leans a little forward, just ahead of where the moon sits in the sky. This small offset has enormous consequences over long stretches of time, and we will come back to that later in this episode. For now, just hold the image. A planet spinning slowly in the dark. A gray moon hanging steady, 239,000 miles away. And the ocean, that thin blue skin covering most of the Earth's surface, stretched into a gentle egg shape by the invisible difference in gravity from one side of the world to the other. Not a violent force, not a sudden event, just a quiet, steady geometry that has been in place since the moon first settled into its orbit billions of years ago. The ocean has been wearing this shape for longer than any mountain has existed, longer than any continent has held its current form. The bulge was there before the first fish, before the first shell, before the first wave broke on any shore. It is one of the oldest shapes on Earth. That oldest shape on Earth has a rhythm to it, a slow, steady pulse. As the Earth turns beneath the moon, different parts of the ocean move through that egg-shaped bulge. When your part of the coast lines up with the bulge, the water rises. That is high tide. When your part of the coast has turned away from the bulge, the water falls back. That is low tide. The ocean itself has not moved far. It is the Earth rotating through a fixed shape that creates the rise and fall you see on the shore. Most places on Earth experience 2 high tides and 2 low tides every single day. Not every 24 hours, though. The moon is also moving through the sky, slowly orbiting the Earth. So the tidal cycle runs about 50 minutes longer than a regular day. Each high tide arrives roughly 50 minutes later than the one before it. If high tide came at noon today, it will come at about 12:50 tomorrow. And 12:50 tomorrow, it will come at about 1:40 the day after. The tides drift forward through the clock, day by day, like a slow wheel turning. The difference in water height between high tide and low tide is called the tidal range. In some places, this range is only a foot or two. The water barely seems to move. In other places, the range can be enormous, and we will visit one of those extraordinary places later in this episode. The tidal range depends on the shape of the coastline, the depth of the water, and how the ocean basin funnels or spreads the incoming tide. The same moon pulls on all of it, but the land shapes what happens next. Now, think about what the ocean is actually made of. That water rising and falling on the shore is not simple stuff. It is a rich, ancient mixture. Seawater is about 96% water and about 3.5% dissolved salts. The most common salt is sodium chloride, the same compound you might sprinkle on food. But the ocean also holds magnesium, sulfur, calcium, potassium, and dozens of other elements in smaller amounts. These minerals did not appear from nowhere. They were carried into the sea over billions of years by rivers washing over rocks, by volcanic vents releasing gases and minerals from deep inside the earth, and by rain slowly dissolving the land and carrying it downhill to the coast. The iron dissolved in the ocean, and the iron locked in the rocks the tide washes over was forged inside a star. Not our sun, an older star that lived and died long before our solar system existed. When that star collapsed and exploded, it scattered heavy elements across space. Iron, nickel, calcium, all of it. These drifted through the galaxy for millions of years. Then gravity pulled them together again, and our solar system formed from that ancient dust. The iron in the rocks the tide touches today was made in a stellar explosion billions of years ago. The water itself has a remarkable origin story. Scientists believe much of Earth's water arrived from space, carried by icy comets and asteroids that bombarded the young Earth during its early history. These objects formed in the cold outer regions of the solar system, where ice could survive. They fell inward and struck the Earth, and over millions of years, they delivered enough water to fill the oceans. The tide that rises on the shore tonight may be made of water that traveled across the solar system before the first continent ever formed. There is something deeply settling about this. The water the moon pulls toward itself is ancient beyond imagining. It has been ocean water, cloud water, glacier water, river water, and rain. It has cycled through the atmosphere and back to the sea more times than any mind can count. And through all of that cycling, the moon has been pulling at it. Every tide that ever rose on any shore was pulled by the same quiet force, the same geometry, the same invisible difference in gravity from one side of the earth to the other. High tide and low tide are not just a coastal event. They are a conversation between the earth and the moon, written in water that came from stars and comets and ancient rain. The minerals in that water were born in the hearts of dying suns. The rhythm of the tides has been keeping time on this planet for billions of years, and twice a day, on almost every shore on Earth, the water rises. It lingers at its peak for a quiet moment, and then, just as gently, it falls back again. The moon does not always pull at the earth from the same distance. Its path around our planet is not a perfect circle. It is an oval shape, a gentle ellipse, and that means the moon spends part of each month closer to Earth and part of each month farther away. At its closest point, which scientists call perigee, the moon sits about 226,000 miles from Earth. At its farthest point, called apogee, it stretches out to roughly 252,000 miles away. That difference is about 26,000 miles. In the scale of the solar system, that sounds small. But when it comes to tides, it changes everything. Gravity follows a very precise rule. When distance doubles, gravitational pull drops to 1/4 of what it was. Scientists call this the inverse square law. It means that small changes in distance create surprisingly large changes in pull. The moon does not have to move very far to tug at the ocean with noticeably more or less force. When the moon is at perigee, its closest point, its gravitational grip on Earth's oceans is stronger. The tidal bulge on the side of Earth facing the moon stretches a little higher. The water rises a little more. The tides at perigee can be roughly 20% higher than average. That is a significant difference amounts, enough to flood beaches that would normally stay dry. When the moon is at apogee, its farthest point, the pole weakens. The tidal bulge flattens slightly. The tides are calmer, lower, quieter. The ocean still rises and falls, but with less drama. Coastal communities that track the tides carefully can feel this difference over the course of a month. The sea behaves differently depending on where the moon sits in its oval path. This is not a coincidence or a mystery. It is gravity doing exactly what gravity always does, following its own ancient rules with perfect consistency. There is something worth sitting with here. The moon's oval orbit is not random. It is the result of gravitational tugs from the sun and from Earth itself, all pulling on the moon in slightly different directions over billions of years. The shape of the moon's path was sculpted by the same forces that shaped the tides. Gravity wrote the orbit, and then the orbit shaped the tides. One force working at different scales, producing effects that ripple all the way down to the waterline on a quiet beach. The moon's distance also affects something called the tidal range, which is the difference in water height between high tide and low tide. When the moon is close, the tidal range grows. When the moon is far, the range shrinks. This is not a dramatic change at most coastlines, but it is real and measurable. Scientists who study the ocean, called oceanographers, can predict these variations years in advance. They use precise measurements of the moon's orbit to build tide tables, which are calendars that tell sailors and coastal planners exactly when the water will rise and how high it will go. These tables are remarkably accurate. The moon's orbit is that predictable. The speed of the moon also changes as it travels along its oval path. When the moon is close to Earth, it moves faster. When it is far away, it slows down. This is another rule of orbital mechanics, the science of how objects move through space under the influence of gravity. A faster moon means it moves through its closest point quickly. A slower moon lingers at its farthest point. This means the periods of stronger tides at perigee are brief, while the calmer tides near apogee last a little longer. The ocean breathes in and out to a rhythm that shifts slightly every month, shaped by the moon's changing speed along its path. All of this happens without any visible connection between the Earth and the moon. There is no rope, no wire, no physical contact of any kind, just the invisible reach of gravity stretching across more than 200,000 miles of empty space, gripping the oceans and pulling them toward the sky. The water does not know why it rises. It simply responds to the force. The moon does not choose to pull. It simply follows the rules that govern all mass in the universe. And yet the result is one of the most reliable rhythms on Earth. Twice a day, on almost every shore, the water obeys. It rises toward a moon it cannot see, drawn by a force it cannot feel, following a pattern that has not changed in billions of years. The distance between the moon and Earth is always shifting, always breathing in and out along that oval path, and the ocean breathes with it. The moon is not alone in this work. Far across the solar system, another force reaches out toward Earth. It is older than the moon. It is larger than anything most of us can truly picture. And every single day, it adds its own quiet pull to the tides that shape our shores. That force comes from the sun. The sun is almost unimaginably large. If you placed the sun next to Earth, you could fit about 1.3 million Earths inside it. 1.3 million. To feel the size of that number, think of it this way. If the sun were shrunk down to the size of a basketball, Earth would be a small peppercorn sitting about 26 yards away, not next to it, not nearby. 26 yards across an open field, a tiny speck beside a glowing orange ball. That is the scale of our solar system, right there in a single image. And yet, despite that enormous size, the sun's pull on our tides is weaker than the moon's. This seems strange at first. The sun is so much bigger. Its gravity shapes the entire solar system. It holds Jupiter and Saturn and every planet in their paths. How could the moon, a small rocky world, pull harder on our oceans than the sun does? The answer is distance. The sun is about 93 million miles away from Earth. That is so far that light, traveling at 186,000 miles per second, takes more than 8 minutes to make the trip. The moon, by comparison, sits only about 239,000 miles away on average. That is roughly 390 times closer to us than the sun. Tidal force does not depend only on how massive an object is. It depends on how much the gravity of that object differs between the near side of Earth and the far side. Scientists call this the tidal gradient, which simply means the change in pull across a distance. Because the moon is so close, its gravity feels noticeably stronger on the side of Earth facing it than on the far side. That difference is what creates the bulge. That difference is what lifts the water. The sun is so far away that its gravity, while powerful overall, feels almost the same on both sides of Earth. The difference between the near side and the far side is smaller. So the tidal gradient is weaker, even though the sun outweighs the moon by an almost absurd amount. The moon wins the tidal contest simply because it is closer. Scientists have calculated that the moon's tidal force on Earth is about 2.2 times stronger than the sun's. The moon pulls roughly twice as hard on our oceans as the sun does. That gap in distance makes all the difference. But the sun is still pulling. Its force is real, and it is not small. The sun's tidal pull is roughly 46% as strong as the moon's. That is nearly half. So while the moon leads this slow, steady work, the sun is always there beside it, adding its own weight to the equation. And here is where the scale of the solar system becomes something you can actually feel in the water. As Earth moves through its year-long orbit around the sun, the angle between the sun and the moon changes constantly. Sometimes the sun, the Earth, and the moon line up nearly in a row. When that happens, the sun's pull and the moon's pull point in the same direction. They combine. The tides grow larger. The water rises higher and falls lower than usual. Other times, the sun and moon sit at a right angle to each other, as seen from Earth. Their poles point in different directions. They work against each other, softening the effect. The tides grow calmer and smaller. This is the sun joining the dance, not leading it, not overpowering it, but adding its enormous, distant weight to the rhythm the moon has already set. Think about what that means. A star 93 million miles away, so large it could swallow more than 1,000,000 Earths, is gently pushing and pulling the water on our beaches every single day. You cannot see it happening. You cannot hear it. But when you stand at the edge of the ocean and watch the tide come in, part of what you are watching is the sun reaching across that vast, cold distance and nudging the sea. The moon began this rhythm, but the sun has always been part of it. Two great bodies in the sky, each pulling in its own way, each shaping the water below. The ocean listens to both of them at once. When the moon and the sun line up together, something remarkable happens at the shore. The water rises higher than it does on most days. It pulls back lower, too. The beach looks different. The wet sand stretches farther out than usual, dark and smooth and wide, gleaming in the light like a mirror laid flat on the earth. This is what sailors and fishermen have called a spring tide for thousands of years. The name has nothing to do with the season. Spring, in this case, comes from an old word meaning to leap or to surge. And that is exactly what the water does. It leaps. The tides during a spring tide are the biggest tides of the month. The high tides are higher. The low tides are lower. The difference between the two, which scientists call the tidal range, grows larger. On a coastline that normally sees a modest rise and fall, a spring tide can feel like the ocean has suddenly decided to show what it is truly capable of. Spring tides happen twice a month. They occur when the moon is full and when the moon is new. During a full moon, the earth sits between the sun and the moon. All three line up. During a new moon, the moon sits between the earth and the sun. Again, all three line up. In both cases, the gravitational poles of the moon and the sun point in the same direction, either together or directly opposite, and their forces add up. The ocean feels both of them at once, and it responds. Stand at a beach during a spring low tide, and you will see things that are usually hidden. Rocks that normally sit underwater appear above the surface, draped in dark green and brown seaweed, slick and glistening. Tide pools form in the hollows of those rocks, small glassy bowls of trapped seawater, holding tiny crabs and sea stars and anemones. The ocean has pulled back its curtain. What was secret is now visible. The exposed exposed seafloor stretches out in shades of gray and brown and deep olive, and the smell of salt and wet stone fills the air. Then there is the other kind of tide, when the moon and the sun sit at a right angle to each other. As seen from Earth, their poles work against each other. Neither one wins. The result is a smaller, gentler tide. Scientists call this a neap tide, from an old English word meaning scanty or lacking. Neap tides are the quiet tides, the modest tides. The tidal range shrinks. High tide does not climb as high. Low tide does not fall as low. The ocean seems almost still by comparison. Neap tides also happen twice a month. They occur during the first quarter moon and the third quarter moon, those half-lit phases when the moon appears as a clean half-circle in the sky. At those moments, the moon, the earth, and the sun form a right angle in space. The sun's pull tugs sideways, softening the moon's effect rather than adding to it. The water responds with calm. Picture a neap low tide on a quiet morning. The light is pale and gray. The sea pulls back only a little, leaving a narrow strip of wet sand at the waterline. The waves are small. The ocean looks almost flat, its surface a dull silver, barely moving. It is the same ocean that surged and retreated during the spring tide just a week before. But now it rests. It breathes slowly. It holds itself close. This 2-week rhythm, spring to neap and back to spring again, runs without pause. It has been running for billions of years. Every month, the ocean swells and calms, swells and calms, following the slow turning of the moon around the earth and the shifting angles between 3 great bodies in space. The pattern is so steady that scientists can predict the tidal range of any beach on Earth, on any day, centuries into the future. What is striking is how much variety this creates along the world's coastlines. 2 beaches on opposite sides of the same continent can have very different tidal ranges, shaped by the local shape of the seafloor and the curve of the land. But both of them follow the same 2-week beat. Both of them feel the spring and the neap. The moon sets the tempo. The sun adjusts the volume. And the ocean, vast and patient and ancient, plays along with both of them, rising and falling in a rhythm older than any living thing on this planet. Beneath that slow, ancient rhythm, something else is happening. Something you cannot see from the shore. While the surface of the ocean rises and falls, the water beneath is moving too. It shifts and turns and flows in long, sweeping currents driven by the same pull that lifts the tide. The tidal cycle is not just a surface event. It goes deep. Most people think of a tide as simply water going up and then coming down. But the full picture is more layered than that. A complete tidal cycle, from one high tide to the next high tide, takes about 12 hours and 25 minutes. That is roughly half a lunar day. A lunar day is the time it takes for the moon to return to the same point in the sky as seen from Earth, which is about 24 hours and 50 minutes. So in a single day, most coastlines experience 2 high tides and 2 low tides. The water rises, peaks, falls, bottoms out, and rises again. Twice, every day, without fail. Those extra 25 minutes matter more than you might expect, because the moon moves through the sky a little slower than the sun. Each tide arrives about 50 minutes later than it did the day before. A high tide that crests at noon today will crest at roughly 12:50 tomorrow, and at 1:40 the day after that. Over the course of a month, the tides drift slowly through the clock, cycling through every hour of the day and night. Fishermen have known this for thousands of years. They planned their work around it. The tide does not keep human hours. It keeps lunar ones. Now think about what is happening below the surface during all of this. As the tide rises, water is not just piling up on the shore. It is flowing in from the open ocean, moving in great horizontal sheets across the seafloor. These flows are called tidal currents, and in some places they move with surprising force. In narrow channels between islands, or in the mouths of rivers, tidal currents can reach speeds of several knots, fast enough to make swimming difficult and sailing tricky. The water is not still. It is always going somewhere. In deeper water, far from the coast, the tidal currents are gentler, but they are still there. Scientists have measured tidal motion thousands of meters below the surface. The moon's pull reaches all the way down. Even the cold, dark water near the ocean floor shifts slightly with each passing tide. It is a slow, quiet movement, barely detectable without sensitive instruments. But it is real. The whole ocean, from surface to floor, breathes with the moon. There is something else happening in the deep water that scientists find especially fascinating. When tidal currents flow over underwater mountains and ridges on the seafloor, they create what are called internal waves. These are waves that travel not on the surface, but inside the ocean, along the boundary between layers of water at different temperatures. The surface may look perfectly calm, but hundreds of meters below, a wave the size of a skyscraper is rolling silently through the dark. Internal waves can travel thousands of kilometers from where they formed. They carry energy from the tidal pull deep into the interior of the ocean, mixing the water as they go. That mixing is important. Cold water from the deep and warmer water from above get stirred together. Nutrients rise. Oxygen spreads. The tidal cycle, working quietly in the dark, helps keep the ocean alive. It is one of the hidden engines of the sea. And then there is the seafloor itself. The constant back and forth of tidal currents shapes the sediment. The fine sand and silt that covers much of the ocean bottom. In shallow coastal areas, tidal currents sort the sediment by size, sweeping fine particles one way and leaving coarser grains behind. Over thousands of years, this creates distinct patterns in the seafloor. Geologists can read these patterns in ancient rock formations and use them to understand what the tides were like millions of years ago. The record of the moon's pull is written in stone. So the tidal cycle is not just a clock. It is a force that reaches from the surface of the sea all the way to the bottom. It moves water, mixes layers, builds waves in the dark, and carves the floor of the ocean over time. Every 12 hours and 25 minutes, the whole system resets. The tide comes in, the tide goes out, and deep below the sparkling surface, the hidden work continues, steady and unseen, the way so much of the ocean's life unfolds. The ocean does not keep the same schedule everywhere. That is one of the quiet surprises of the tidal world. The moon pulls on all the oceans at once, the seafloor, the depth of the water, and the outline of each coastline all change how the tide arrives. The result is that different places around the world experience the tides in very different ways. Most coastlines on Earth experience 2 high tides and 2 low tides every day. This pattern is called a semidiurnal tide, which simply means 2 tides per day. The east coast of North America follows this pattern. So does the coast of Western Europe. Twice each day, the water rises. Twice each day, it falls. The timing shifts a little each day, about 50 minutes later than the day before, because the moon is slowly moving along its orbit as the Earth turns beneath it. But the rhythm stays steady. 2 highs, 2 lows, day after day. Some coastlines, though, experience only 1 high tide and 1 low tide each day. Scientists call this a diurnal tide, meaning 1 tide per day. Parts of the Gulf of Mexico follow this pattern. So do some coastlines in Southeast Asia and along the shores of the Gulf of Tonkin. In these places, the water rises once, then falls once, and that is the full cycle for the day. The difference comes down to the shape of the ocean basin and how it responds to the moon's pull. Some basins are tuned, in a sense, to resonate with 1 tidal pulse per day rather than 2. There is also a third pattern, one that falls between the other 2. Some coastlines experience what scientists call mixed tides. In this pattern, there are still 2 high tides and 2 low tides each day, but they are not equal. 1 high tide is noticeably taller than the other. 1 low tide drops much farther than the other. The coast of California follows this pattern. So does much of the Pacific coast of North America. On these shores, the tides have a kind of unevenness to them. A tall wave and a shorter one. A deep retreat and a shallower one. All within the same day. This variety exists because the ocean is not a simple bowl of water sitting still. It is a complex, moving system with basins of different shapes and depths, all responding to the same gravitational force in slightly different ways. The moon's pull is consistent, but the ocean's answer to that pull depends on local conditions. It is like striking the same note on different instruments. The source of the sound is the same, but each instrument responds in its own voice. The size of the tides also varies enormously from place to place. In some parts of the open ocean, far from any coastline, the tidal range, the difference between high and low tide, is less than half a meter. The water barely seems to move at all, but near certain coastlines, especially where the shape of the land funnels the water into a narrowing bay or inlet, the tidal range can grow to extraordinary heights. The water has nowhere to spread out, so it piles up instead. The timing of the tides also shifts as you move around the globe. High tide does not arrive everywhere at the same moment. The tidal bulge, that gentle swelling of water pulled toward the moon, moves across the ocean surface as the Earth rotates. It travels like a slow wave, arriving at each coastline in turn. Scientists have mapped these arrival times carefully, and the patterns are striking. In some ocean basins, the tidal wave circles around a central point, like water swirling slowly around a drain. That central point, called an amphidromic point, experiences almost no tidal rise or fall at all. The tide rotates around it, but never quite reaches it. There are roughly a dozen of these amphidromic points scattered across the world's oceans. They sit quietly at the center of great rotating tidal systems, calm and still while the water wheels around them. The North Sea, that shallow body of water between Britain and mainland Europe, has its own amphidromic point near its center. The tides of the North Sea rotate counterclockwise around it, arriving at different shores at different times. All of this variety, the two-tide coasts and the one-tide coasts, the mixed patterns and the rotating systems, comes from a single source. One moon pulling steadily on one ocean. But the ocean is old and deep and shaped by millions of years of shifting land. It does not respond simply. It responds with all the complexity it has gathered over time. And so, the tides of the world are not one rhythm, but many, all beating together, all tracing back to that same quiet pull from above. Among all the places on Earth where the ocean meets the land, one stands apart, tucked into the northeastern corner of North America, between the Canadian provinces of Nova Scotia and New Brunswick, sits a long, is not the largest bay in the world. It is not the deepest, but it holds a record that no other place on Earth can match. The tides here rise higher than anywhere else on the planet. At the bay's deepest reaches, the water can rise more than 16 meters between low tide and high tide. That is roughly the height of a 5-story building. At low tide, the seafloor sits exposed and wide, covered in red-brown mud, stretching out like a vast open plain. Fishing boats rest on their sides in the mud, waiting. Then the water returns. It comes back fast and steady, filling the bay from the bottom up, climbing the red cliffs, swallowing the mud flats whole. Within hours, those same boats float again, lifted gently by billions of tons of moving water. The reason the Bay of Fundy does this comes down to shape and timing. The bay is long and narrow, like a funnel. As the ocean's tidal bulge pushes water toward the coast, the bay's shape forces all of that water into a tighter and tighter space. The water has nowhere to go but up. This effect, where a body of water's shape amplifies the tide, is called resonance. It works the same way sound resonates inside a musical instrument. The shape of the space determines how the energy moves through it. But resonance alone is not the whole story. The Bay of Fundy has a natural rhythm of its own. Every body of water, from a bathtub to an ocean, has a natural rocking period. The time it takes for water to slosh from one end to the other and back again. Scientists call this a sage, which means a back and forth rocking motion. The Bay of Fundy's natural rocking period is almost exactly 12.5 hours. The tidal cycle, driven by the moon, repeats roughly every 12.5 hours as well. These two rhythms match almost perfectly. They reinforce each other. The way two people pushing a swing in perfect time send it higher and higher with each push. The result is a tide of extraordinary size. This kind of matching between a natural rhythm and an outside force is called resonance, and it is one of the most powerful forces in nature. It shows up in bridges and buildings, in musical strings, in the orbits of planets. Here in the Bay of Fundy, it shows up in the sea itself, amplifying the moon's gentle pull into something enormous and visible and deeply impressive. roughly 100 billion tons of seawater flow in and out of the Bay of Fundy with each tidal cycle. That number is almost impossible to hold in the mind. It is more water than the combined flow of every freshwater river on Earth during the same period. The movement stirs the water deeply, pulling cold, nutrient-rich water up from the bottom. This upwelling feeds enormous blooms of tiny sea creatures, which in turn feed fish, which in turn feed whales. The Bay of Fundy is one of the best feeding grounds in the North Atlantic, and the tides are the reason. The red cliffs along the bay's shores tell another part of the story. They are made of ancient sandstone, soft and crumbling, carved by centuries of tidal action into strange shapes. Tall columns of rock, called sea stacks, rise from the water, left behind as the softer rock around them wore away. The tides here do not just move water. They carve the land slowly and steadily, reshaping the coastline with every cycle. Nearby, the Minas Basin, the innermost arm of the Bay of Fundy, sees some of the most extreme tidal ranges of all. The water there can rise and fall by more than 17 meters. Twice a day, every day, the basin empties and fills. The mud flats that appear at low tide are rich with clams and worms and small creatures, drawing thousands of shorebirds that time their arrivals to match the tides. The Bay of Fundy is not separate from the larger story of the tides. It is one of the clearest examples of what the tides can become when the right geography meets the right timing. The moon pulls. The ocean responds. And in one long, narrow bay on the edge of Canada, that response becomes something extraordinary. The Bay of Fundy holds the record for the highest tides on Earth. But the story of where land meets the tide does not end there. Across the planet, the tides push against coastlines in ways that are surprising, sometimes violent, and always worth paying attention to. Some of the fastest tidal currents in the world move through narrow channels between islands. In the Pentland Firth, the stretch of cold water between northern Scotland and the Orkney Islands, tidal currents can reach speeds of more than 16 kilometers per hour. That is faster than most people can run. The water does not look like a gentle sea in those moments. It churns and boils, forming standing waves and whirlpools that sailors have feared for centuries. The narrow gap between the land masses squeezes the tidal flow, and the water accelerates the way air rushes through a tight doorway. Similar forces create the Saltstraumen, a narrow channel on the coast of Norway. It holds the record for the strongest tidal current on Earth. Water rushes through a channel only about 150 meters wide, and the current can reach nearly 40 kilometers per hour. Massive whirlpools form and dissolve as the tide shifts. The Saltstraumen is not a quiet place. The roar of the water is constant, and yet somehow fish gather there in great numbers. Drawn by the nutrients the current stirs up from the seafloor. Even in the most extreme places, life finds a way to use what the tides provide. Not all tidal extremes are about speed or height. Some are about time. In certain parts of the Gulf of Mexico, the tidal cycle behaves in an unusual way. Most coastlines experience 2 high tides and 2 low tides every day. But along parts of the Gulf Coast, there is only 1 high tide and 1 low tide in a full day. Scientists call this a diurnal tide, meaning a once-daily tide. The shape of the Gulf, combined with the way the water sloshes back and forth in that enclosed basin, smooths 2 tidal peaks into one. The result is a coastline where the water rises and falls just once in 24 hours, slow and steady, like a single long breath. The lowest tides can be just as dramatic as the highest ones. When the tide pulls back far enough, it reveals a hidden world. Rocky shores that are normally underwater become exposed. Tide pools form in the hollows of the rock, small trapped pockets of seawater left behind as the ocean retreats. These pools can sit in the open sun for hours. The water inside them warms. The salt concentrates as some of the water evaporates. The creatures living there, small crabs, sea anemones, starfish, and snails, must survive conditions that shift from one extreme to another every few hours. The lowest tides of the year, which happen during the strongest spring tides, expose the deepest pools and the creatures that rarely see open air. Some coastlines experience tidal bores, which are waves that travel upstream into rivers is strong enough. The River in China produces one of the most powerful tidal bores on Earth. During the highest tides of the year, a wall of water up to 9 meters tall surges up the river at speeds of around 40 kilometers per hour. The sound arrives before the wave does, a deep rumble that builds into a roar. People travel from across China to watch it from the riverbanks. The wave can be heard long before it is seen. It is one of the most dramatic things the tides produce anywhere on the planet. The Amazon River in Brazil also produces a tidal bore called the Pororoca. It is not as tall as the bore, but it travels much farther inland, sometimes pushing more than 800 kilometers up the river. The Pororoca can last for 30 minutes or more as it passes a given point. It carries debris, uproots trees along the banks, and reshapes the riverbed as it moves. Some surfers have ridden the Pororoca for extraordinary distances, carried far inland by the force of the incoming tide. These records and extremes are not random. They all trace back to the same source. The moon pulls on the ocean responds, and when the shape of a coastline, the depth of a channel, or the curve of a river mouth lines up with that pull in just the right way, the result can be something that stops you in your tracks. The tides are the same force everywhere, but the land gives them 1,000 different voices. Not every voice the tide finds is loud. Some are barely a whisper. Between the crashing waves and the dry land above, there is a thin strip of shore that belongs to neither world. Scientists call it the intertidal zone. It is the band of coastline that sits underwater at high tide and exposed to open air at low tide. Twice a day, this narrow stretch of rock and sand gets soaked, then dried, then soaked again. Most creatures could not survive that kind of change. But the animals and plants that live here have spent millions of years learning exactly how to do it. Look closely at a rocky shoreline at low tide. What you see is not random. The creatures are sorted into bands, almost like rings on a target. The highest band, just barely touched by the tallest waves, is home to small gray snails called periwinkles and a crust of dark lichen. Below that, a zone of barnacles covers the rock like a rough white carpet. are still, mussels cluster in dense blue-black mats, their shells pressed tight together, and at the very bottom, where the water barely retreats, sea stars and anemones wait in shallow pools. Each creature lives in exactly the zone it can handle. Move it up or down even a little, and it struggles. This sorting has a name. Scientists call it zonation, which simply means the way living things arrange themselves in layers based on the conditions they can tolerate. The tides create those conditions. The tides draw the lines. Every band of life on that rock is a record of how high the water rises and how long the air stays dry. The moon, pulling from 250,000 miles away, is the force that wrote those lines. Barnacles are one of the great survivors of the tidal zone. At high tide, they open their shells and sweep tiny food particles from the water with feathery legs. At low tide, they seal themselves shut with a pair of small plates, trapping a tiny drop of moisture inside. They can survive hours of heat, cold, and drying wind in that sealed state. A barnacle can live for years on a rock that bakes in summer sun and freezes in winter spray. It simply waits. The tide always comes back. Mussels use a different trick. They anchor themselves to rock with threads called byssal threads, which are stronger than steel wire of the same thickness. A mussel can hold on through waves that would knock a person flat. When the tide drops, they close their shells and hold still. When the tide returns, they filter seawater for tiny particles of food. A single mussel can filter more than a liter of water every hour. A dense bed of mussels cleans enormous amounts of seawater every single day, quietly doing work that benefits the whole coastal ecosystem. Tide pools are perhaps the most magical detail in all of this. When the tide pulls back, it leaves behind small pockets of seawater trapped in hollows in the rock. These pools are like tiny windows into the ocean. Sea anemones open their soft petals in the still water. Hermit crabs drag their borrowed shells across the sandy bottom. Small fish dart between the rocks. The colors are extraordinary up close. The deep purple of a sea urchin, the bright orange of a starfish, the pale green of sea lettuce clinging to the rock. All of it exists because the tide came in, left left a little behind and went back out. The temperature inside a tide pool can swing wildly in a single day. On a hot afternoon, the water in a shallow pool can warm to temperatures that would stress most ocean animals. On a cold night, it can drop sharply. The creatures that live in pools have evolved to handle this. Their bodies adjust. Their chemistry shifts. Scientists study tide pool animals to understand how life copes with rapid change. And what they find there has helped inform research far beyond the shoreline. Sea stars, those slow and ancient hunters, play a special role in keeping the tidal zone balanced. They eat mussels. Without sea stars, mussels would spread and crowd out nearly everything else. When scientists removed sea stars from a stretch of shoreline in an experiment, the mussel population exploded and the diversity of the whole zone collapsed. One animal, moving slowly across a wet rock, was quietly holding the whole community together. The tidal zone is small. You could walk across it in a few steps, but inside that narrow strip, life has found 1,000 ways to keep going. The tide sets the rhythm. The creatures follow it, and in following it, they have become some of the most resilient living things on Earth. The animals of the tidal zone have been reading the sea for far longer than humans have. Long before any person wrote down an observation or built an instrument, creatures were already tracking the tide with their bodies. And when humans finally started paying close attention, they found that animals had been keeping records all along. The fiddler crab is one of the most studied examples. These small, quick crabs live along mudflats and sandy shores. They come out to feed when the tide is low and retreat when the water rises. But here is what surprised scientists. Fiddler crabs keep this rhythm even when you take them away from the ocean entirely. Bring one into a laboratory. Set it in a tank with no tides, no waves, no salt air, and it will still become active, and still, at the same times, it would have been active on the shore. The crab carries a clock inside its body. That internal clock runs on a cycle of roughly 12.5 hours, matching the tidal rhythm almost exactly. Scientists call this a circadian rhythm, which simply means a biological cycle tied to the tides. This This discovery helped reshape how biologists think about time and living things. For a long time, scientists focused on the 24-hour day as the main clock that life runs on. Light and dark, sunrise and sunset. But coastal animals showed that another clock exists, one tuned not to the sun, but to the moon. The two clocks can run at the same time inside the same animal. A fiddler crab responds to both. It knows when the tide is low. It also knows when the sun is high. Both pieces of information shape what it does. Researchers spent decades trying to find where this tidal clock lives inside the animal's body. With the daily clock, scientists eventually found specific clusters of cells in the brain that act as timekeepers. The tidal clock proved harder to locate. Evidence suggests it may be spread across multiple systems in the body, rather than sitting in one single place. The search is still ongoing. The fiddler crab, small enough to fit in your palm, is still teaching scientists things they do not fully understand. Other animals show the same kind of inner awareness. The California grunion is a small silver fish that times its entire breeding cycle to the tides. On certain nights in spring and summer, just after the highest tides of the month, grunion ride the waves onto California beaches by the thousands. The females dig into the wet sand and lay their eggs. The males fertilize them right there on the beach. Then both fish ride the next wave back out to sea. The eggs sit buried in the sand, safe above the waterline, until the next round of high tides washes over them 2 weeks later. That surge of water triggers the eggs to hatch. The timing is so precise that biologists can predict grunion runs weeks in advance. The fish have no calendar. They read the sea itself. Horseshoe crabs follow a similar pattern. These ancient animals, whose body shape has barely changed in hundreds of millions of years, come ashore to spawn on the highest tides of late spring. They gather on beaches along the Atlantic coast of North America in numbers that can darken the sand. Their eggs become a critical food source for migrating shorebirds, which time their own long flights to arrive, just as the crabs do. The crab reads the tide. The bird reads the crab. One signal moves through the whole system. early human observers noticed these patterns long before they understood them. Fishermen along the coast of ancient Greece wrote about how sea urchins seemed to grow fuller and more active around the full moon when tides run strongest. Aristotle noted this in his writings more than 2,000 years ago. He did not know about gravitational pull or tidal cycles in any modern sense, but he was watching carefully, and he saw that the moon and the sea and the animals were all moving together in some way he could not yet explain. That careful watching was the beginning. Humans are not born with a tidal clock the way a fiddler crab is. We had to learn by looking. We had to sit on shores, watch the water, and notice that the creatures around us seemed to know something we did not. The animals were the first teachers. Their behavior pointed toward the moon long before any human instrument could measure its pull. And in studying them, scientists have come to understand that the tide does not just shape the shore. It reaches inside living things and sets them ticking. The tide reaches inside living things, but it also reaches somewhere far stranger. It reaches beneath the ice. At the bottom of the world, Antarctica holds the largest sheet of ice on Earth. Some of that ice sits on solid ground, but enormous sections of it float. They extend out from the continent and rest on the surface of the sea. Scientists call these floating shelves of ice shelves, and they cover an area larger than Mexico. Beneath them, the ocean is dark and cold and completely hidden from the sky. And yet, even there, the tide moves. The moon's pull does not stop at the edge of open water. It reaches under those vast frozen roofs and lifts the sea beneath them. The water rises and falls on its usual schedule, twice a day, just as it does on any open beach. But here, the rising water has nowhere to go except up. It pushes against the underside of the ice. The ice flexes. It bends. Slowly, gently, the entire floating shelf breathes in and out with the rhythm of the tide. This bending is not visible from above. Standing on the surface of an ice shelf, you would feel nothing. The ice is hundreds of meters thick in places, but instruments placed on the surface can detect the movement. The shelf rises and falls by as much as a meter or more with each each tidal cycle. That is a slab of ice the size of a small country, lifting and settling like a sleeping chest. Scientists find this remarkable for a specific reason. That bending creates stress inside the ice. Stress, over time, creates cracks. And cracks, over long periods, can cause pieces of the ice shelf to break away and float out to sea. The tide, patient and constant, is one of the forces that slowly shapes the edges of Antarctica. The moon, from 384,000 kilometers away, is helping to carve the frozen continent. The surprises do not stop at the poles. Beneath the surface of the open ocean, the tide creates something most people never think about. It creates internal waves. These are not waves on the surface of the water. They are waves that form deep inside the ocean, where layers of water at different temperatures meet. When the tide pushes water over an underwater ridge or a seamount, a mountain on the ocean floor, it disturbs those layers. The disturbance travels as a wave, sometimes hundreds of meters tall from trough to crest, moving silently through the dark water far below any ship. These internal waves can be taller than a skyscraper. No one on the surface would ever know they were there. There is something else the tide does that most people would not expect. It moves the solid ground, not just the ocean, the land itself. The same gravitational pull that lifts the sea also tugs on the rock beneath your feet. The solid earth deforms slightly as the moon passes overhead. The ground rises by as much as 30 centimeters in some places during a tidal cycle, then settles back down. This is called the earth tide, and it happens everywhere, all the time, whether you are standing on a beach or in the middle of a continent, thousands of kilometers from the nearest ocean. The ground beneath a city like Chicago or Paris rises and falls each day, slowly, silently, completely undetectable without precise instruments, but real. Physicists who study this find it quietly astonishing. We tend to think of rock as fixed and permanent. We think of the ground as the one thing that does not move. But the moon does not agree. It pulls on everything with mass. Rock has mass, so the rock responds. This means the tide is not a coastal event. It is a planetary one, It touches the ice shelves at the poles, the deep layers of the ocean, the bedrock under every city, the water in underground rivers, and the living cells of every creature on the shore. The same force that makes a wave break on a beach in California is also flexing the Antarctic ice and lifting the streets of Paris by the width of a hand. Most people picture the tide as something that happens at the water's edge. A line of foam moving up a beach, a harbor filling and emptying. But the moon's pull is not that polite or that local. It reaches into every part of this planet. It squeezes and stretches and lifts and releases. The earth, in response, moves, all of it together, every single day. And here is something that will stay with you long after you fall asleep tonight. The moon is leaving us, not quickly, not in any way you would notice in a lifetime, or even in 1,000 lifetimes, but slowly, steadily, measurably, the moon drifts a little farther from Earth each year. Scientists have measured this with lasers. Astronauts who walked on the moon left small mirrors on its surface. Researchers on Earth fire laser beams at those mirrors and time how long the light takes to return. The answer tells them exactly how far away the moon is. And year after year, that number grows. The moon moves about 3.8 centimeters farther from Earth every single year. That is roughly the width of 2 fingers held together. It does not sound like much, but over billions of years, it adds up to something enormous. This slow drift is connected directly to the tides. The same force that pulls ocean water into a bulge also acts like a gentle brake on the whole Earth-Moon system. As the moon pulls the ocean forward, the ocean's bulge pulls back on the moon. That tiny tug, repeated endlessly, pushes the moon into a slightly higher orbit. A higher orbit means a wider circle. A wider circle means more distance. So the tides themselves are slowly, gently pushing the moon away. The ocean is doing this. The water you watch rolling up a beach is part of a process that has been nudging the moon outward for 4 billion years. And as the moon drifts away, its pull on Earth grows slightly weaker. Weaker pull means smaller tides. Scientists believe that when the moon was young and much closer, the tides it raised were enormous. ancient seas with tremendous force. Those ancient tides stirred the young ocean constantly. They mixed nutrients. They moved heat. Some researchers believe those violent early tides may have helped create the conditions where life first began to form. The churning of water, the mixing of chemicals, the cycling of energy. The moon's closeness may have helped spark the living world. That connection runs deep. Life and tides have been linked from the very beginning. As the moon moves away, something else changes too. Earth's spin slows down. The two processes are tied together. The same tidal friction that pushes the moon outward also acts as a drag on Earth's rotation. Earth is very slowly spinning down, like a top losing its energy. A day on Earth is getting longer. Not by much. About 1.4 milliseconds per century. You will never feel it. But it is real, and it is measurable, and it has been happening since the planet was young. Scientists who study ancient rocks and ancient coral fossils have found evidence that a day on Earth was once only about 22 hours long. The moon was closer then. The tides were stronger. The drag was greater. Earth spun faster. So the length of your day is a record of the moon's history. Every sunrise comes a tiny fraction of a second later than it would have if the moon had stayed put. This is how systems connect. The moon's gravity shapes the ocean. The ocean's response pushes the moon away. The moon's drift weakens its pull. The weakening pull slows the tides. The slowing tides reduce the drag on Earth. Earth's spin changes. The length of the day changes. Each piece moves the next, like a chain of falling dominoes stretching across billions of years. And none of it is random. It all follows the same laws of gravity and motion that govern every planet, every moon, every star in the universe. The same physics that governs the moon's slow drift from Earth also governs moons around Jupiter and Saturn. It governs binary stars orbiting each other across vast distances. It is one of the deep rules of the cosmos, playing out quietly here in our own backyard, in the rise and fall of the sea. The moon will not leave us entirely. Long before it drifts far enough to matter, the sun will change. The whole solar system will change. cosmic time. The moon is still close enough to move our oceans, still close enough to light our nights, still close enough to feel like it belongs to us. And every tide that rolls in, every wave that lifts and falls, carries within it the faint echo of that ancient, ongoing conversation between the earth and its moon, pulling, drifting, slowing, breathing together. That conversation between the earth and its moon does not only play out in the water, it plays out in stone, in sand, in the slow, patient reshaping of every coast on earth. The tide is not just a visitor, it is a sculptor. Every time the tide rises, it carries energy. That energy pushes water against rock, against sand, against clay cliffs and muddy shores. Every time the tide falls, it pulls material back out to sea. This happens twice a day, every day, year after year, century after century. Over long stretches of time, that patient repetition carves the world. Rock is hard, but water is persistent. Tidal water works its way into tiny cracks in coastal cliffs. As the water moves, it widens those cracks. Over hundreds of years, whole sections of cliff can break away and fall into the sea. This process is called erosion, which simply means the wearing away of land by water or wind. Tidal erosion has reshaped entire coastlines over thousands of years. Headlands that once jutted far out into the sea have been worn down to stumps. Bays that were once shallow inlets have grown wide and deep. Some of the most dramatic examples of tidal erosion sit along the coasts of England and Ireland, the white chalk cliffs of Dover, those tall, pale walls rising straight from the sea, lose a little of themselves each year to the tide and the waves. Scientists estimate that in some places, those cliffs retreat by about 1 centimeter every year. That sounds small, but over 1,000 years, that adds up to 10 meters of solid rock gone. The tide also builds. It does not only take away. When tidal water slows down, it drops the material it has been carrying. Sand, silt, and tiny particles of shell and rock settle out of the water and pile up. Over time, these deposits form new land. Tidal flats, those wide stretches of soft, muddy ground that appear at low tide, are built this way Salt marshes, those dense green wetlands that fringe so many coastlines, grow up from tidal deposits over centuries. They are some of the most productive places on Earth, full of birds, fish, crabs, and plants that have learned to live in the rhythm of the tides. River mouths are shaped by tides too. Where a river meets the sea, the incoming tide pushes back against the river's flow. This creates a zone where fresh water and salt water mix. These places are called estuaries, and they are shaped by the constant push and pull between river current and tidal force. The estuary's shape, its depth, its width, all of it reflects the balance between those two forces. Change the tide, and the estuary changes with it. Over very long timescales, sea level itself changes. During ice ages, so much water freezes into glaciers on land that sea levels drop by more than 100 meters. Coastlines shift far out toward the sea. Tidal zones move with them. Then the ice melts, sea levels rise, and the tide reclaims land that was dry for thousands of years. Scientists can read this history in the layers of sediment along ancient coastlines, in the drowned forests that sometimes appear at low tide along the coasts of Wales and Scotland. Their dark stumps still standing where they fell thousands of years ago when the land was higher and the sea was farther away. Right now, sea levels are rising again. They are rising because the climate is warming and glaciers are melting. As sea levels rise, tidal zones shift inland. Low-lying coastlines that were once visited by the tide only at high water are now flooded more often and more deeply. Salt marshes are being drowned before new ones can form farther inland. Sandy beaches are being pushed back. The same tidal forces that have always shaped coastlines are now working in a world where the sea is a little higher than it was a century ago and rising still. The coastline you see today is not the coastline that existed 1,000 years ago. And it is not the coastline that will exist 1,000 years from now. The tide is always working, always carrying, always carving, always building somewhere new even as it wears something old away. There is something deeply calming in that thought. The world is not fixed. It is not finished. It is always in the middle of becoming something else, grain by grain, wave by wave, the same patient forces that shaped the cliffs and the marshes and the drowned forests are still at work tonight, quietly, steadily, as the water rises and falls along every shore on earth. The tide does more than shape the shore. It reaches far out to sea, past the breakers, past the shallow shelf, and down into the deep. Tidal currents, the slow, steady flows of water driven by the moon's pull, move through the ocean like rivers with no banks. You cannot see them from the surface, but they are there, carrying heat and cold and life across enormous distances. Near the coast, tidal currents can be powerful enough to feel. Sailors have known this for centuries. The water in a narrow channel between two islands can run fast enough to overturn a small boat when the tide turns. The color of the water changes in those places. It shifts from the flat gray-green of calm water to a churning, broken white where the current runs hard over a shallow ridge. Light catches the surface differently there. It scatters and splinters. The sea looks alive in a way it does not in calmer water. Out in the open ocean, tidal currents slow down. They spread out across vast distances and become something quieter. But they do not stop working. As these currents move, they drag water up from the deep in a process called upwelling. Cold water from far below the surface rises toward the light. That cold water is rich in nutrients, the tiny dissolved minerals that feed the smallest living things in the sea. Where upwelling happens, the ocean blooms. The surface of the sea in an upwelling zone takes on a different color. It turns a deeper, richer blue-green. Sometimes it looks almost turquoise in bright sunlight. That color comes from the tiny plants called phytoplankton, which are microscopic organisms that drift near the surface and use sunlight to grow. They are so small you cannot see a single one, but when millions of them gather, they tint the water. From above, from a satellite looking down, these blooms appear as swirling green and blue clouds painted across the ocean's face. Tidal currents help stir the deep ocean in another way too. When a current flows over an underwater mountain range or ridge, it creates internal waves. These are waves that move not on the surface, but deep inside the ocean, along the boundary between warm water near the top and cold water below. help mix the ocean's layers. Without that mixing, the deep ocean would grow colder and more still over time. The heat carried from the tropics by surface currents would not circulate as well. The whole system of ocean circulation, which moves warmth around the planet and helps regulate the climate, depends in part on the moon's quiet, tireless pull. Deep below the surface, where no sunlight reaches at all, the ocean is a world of permanent darkness. The water there is near freezing. The pressure is immense, and yet life exists. Strange, pale fish with wide eyes drift through the black. Creatures that glow with their own cold light move slowly through the dark. That glow, called bioluminescence, is produced by chemical reactions inside the animal's body. It is one of the most beautiful things in the natural world. A blue-green shimmer in total darkness, like a tiny star drifting through an underwater sky. Tidal mixing helps bring nutrients down to those depths and pull cold, mineral-rich water back up. Even in the deepest places, the moon's influence is felt. The rhythm of the tides reaches all the way down, faint but real. A gentle pulse that runs through the entire ocean from surface to floor. There is something worth sitting within that image. The moon hangs in the sky, cold and silent, more than 200,000 miles away, and yet its gravity reaches down through miles of open water, through the dark and the cold and the pressure, all the way to the ocean floor. It stirs the deep. It feeds the smallest living things. It helps warm water travel from the equator toward the poles. It keeps the whole ocean breathing. Light tells part of this story. The shimmer of a tidal current over a shallow bar. The blue-green bloom of phytoplankton seen from space. The cold glow of a deep-sea creature drifting in the dark. Each one is a sign of the same force at work. The moon pulling, the water moving, the ocean alive in ways that reach far beyond what any shoreline can show. The moon does more than move the water. It slows the earth itself. Right now, as you rest, the planet beneath you is spinning. It has been spinning for more than 4 billion years, but it is not spinning as fast as it once did. Long ago, a single day on Earth lasted only about 6 hours. The planet turned at a dizzying pace, far faster than anything alive today could recognize. Over time, that spin has slowed, and the moon is the reason why. Here is how it works. As the moon pulls on the oceans, it creates those two great bulges of water we have talked about. Those bulges do not sit perfectly still. The earth rotates beneath them, and as it does, there is friction. The water drags against the seafloor. The tides push and pull against coastlines and shallow shelves. All of that resistance acts like a very gentle break, not something you could feel in a single lifetime, but across millions and billions of years, it adds up to something real. Scientists call this process tidal breaking. It is the gradual slowing of Earth's rotation caused by the friction of the tides. Each century, the length of a day grows by about 1.4 milliseconds. That sounds like almost nothing. And in any single human life, it is. But over the deep history of the planet, those tiny fractions have added up to hours. The 6-hour day of ancient Earth has stretched, slowly and steadily, into the 24-hour day we know now. There is something almost musical about that. The moon pulling on the sea dragging against the land slowing the spin of the whole planet. Each piece connected to the next, a long, slow rhythm playing out across geologic time. And the Earth does not keep all that lost energy to itself. It passes it along. As Earth's spin slows, the moon drifts outward. The same tidal forces that break the planet also push the moon into a slightly wider orbit. Every year, the moon moves about 1.5 inches farther away from Earth. That is roughly the same rate at which your fingernails grow. Slow, quiet, steady. The moon is not leaving. It is just easing back, very gradually, the way a dancer might step away after a long, close turn. This transfer of energy between Earth and moon is one of the most elegant exchanges in the solar system. Nothing is lost. The spin slows, and that energy flows outward, carried away in the moon's expanding path around us. Now think about what that means in terms of sound. Not sound in the way we usually think of it, as something moving through air, but vibration. The tides create real physical stress on the Earth's crust. As the ocean water piles up and retreats, the solid ground beneath it actually flexes. Scientists can measure this. They call it the solid Earth tide, and it is happening right now, beneath every continent, beneath every city, beneath every sleeping person on the planet. If you could somehow hear that flexing, it would be a sound so low and slow, it would fall far below the range of human hearing. Scientists call sounds like this infrasound, meaning sound with a frequency too low for our ears to catch, but instruments can detect it. And when researchers convert those readings into something audible, the earth hums. A deep, slow, almost breathing sound. The planet itself bending gently under the pull of the moon. Earthquakes produce similar signals. So do ocean waves. So do storms. The earth is never truly silent. It vibrates constantly, a low chorus of forces pressing and releasing against each other. The tides are part of that chorus. The moon's gravity reaches down through the water, through the seafloor, into the rock itself, and the rock responds. It flexes, it breathes, it hums. There is a kind of comfort in that image. The moon, hanging cold and pale in the sky, is not separate from the earth. It is in constant conversation with it. A conversation written in the slow drag of water, the flecks of stone, the lengthening of days, the outward drift of a silver orbit. The earth listens. The earth responds. And the whole system keeps moving, keeps adjusting, keeps finding its balance across time. You are resting on a planet that is always in motion, always in dialogue with the sky above it. The moon pulls, the earth turns, the tides rise and fall. And somewhere in all of that, there is a rhythm so old and so steady that it has been playing since before the first living thing ever opened its eyes. That conversation between the earth and the moon has a name. Scientists call it tidal locking. And it is one of the most elegant outcomes in all of orbital mechanics. The branch of science that studies how objects move through space under the pull of gravity. Tidal locking happens when one world's gravity slows the spin of another world until that spin matches its orbit exactly. The moon is the most familiar example. Long ago, the moon spun freely, turning on its own axis the way the Earth does now. But the Earth's gravity pulled on the moon's slight bulge, creating a slow, steady friction across millions of years. That friction acted like a gentle brake. The moon's spin gradually slowed and slowed and slowed until at last it matched the time it takes the moon to travel once around the Earth. That journey takes about 27.3 days, and now the moon's rotation takes exactly 27.3 days too. The result is something remarkable. The moon always shows us the same face, the same craters, the same pale gray plains, the same familiar patterns that people have looked up at for all of human history. There is a whole other side to the moon, a far side that no human eye ever saw until a spacecraft flew around it in 1959. That far side is not dark, despite what people sometimes say. It receives just as much sunlight as the near side. It is simply always turned away from Earth. It is a face we have never seen from the ground. The mathematics behind tidal locking are clean and precise. The ratio is exactly 1:1. One rotation for every one orbit. The universe arrived at this ratio not through chance, but through physics working patiently over time. Gravity, distance, mass, and spin all fed into the same equation, and the answer came out perfectly whole. There is something deeply satisfying about that. A fraction that reduces to 1. This same process has happened across the solar system. Many of the large moons orbiting Jupiter and Saturn are tidally locked to their planets. Pluto and its moon Charon are locked to each other, both showing the same face at all times, turning together like two dancers who never let go. Scientists call this mutual tidal locking. Both worlds have slowed to match each other. They face each other across a fixed distance, turning in perfect unison through the cold dark of the outer solar system. The Earth itself is slowly moving toward a similar fate. The moon's tidal friction is gradually slowing the Earth's rotation. Each year, the day grows slightly longer by about 1.4 milliseconds per century. That sounds like almost nothing, and right now it is. But given enough time, billions of years from now, the Earth's day would lengthen until it matched the moon's orbital period. The Earth and moon would face each other permanently, locked in that same quiet 1:1 ratio. the tides as we know them would essentially stop. The ocean would settle into a permanent bulge, fixed in place, no longer rising and falling. The rhythm that has shaped coastlines and guided life for billions of years would go still. Scientists can calculate all of this with extraordinary precision. They can predict the position of the moon to within a few centimeters using laser beams bounced off reflectors left on the lunar surface by Apollo astronauts. They can measure the moon's outward drift, about 3.8 centimeters per year, with instruments sensitive enough to detect changes smaller than a human hair. The numbers are not guesses. They are measurements, checked and rechecked, written in the language of physics that does not change. What makes tidal locking so beautiful is that it is not a coincidence or a curiosity. It is the natural end state of any two worlds that spend enough time close to each other. Gravity always seeks this balance. It always works toward that clean, simple ratio. Given time, it always finds it. The universe has a preference for order, for systems that settle into steady, repeating patterns. Tidal locking is one of those patterns. It is gravity finishing what it started. And so the moon hangs above us, its near side silver and familiar, its far side forever hidden, its face frozen in a pose it has held for hundreds of millions of years. It is not frozen by cold. It is frozen by mathematics, by the patient arithmetic of gravity working across time. The same force that lifts the oceans, bends the rock, and lengthens the day also reached up and stilled the moon's spin and fixed its gaze upon us. The moon does not wander. It watches, always the same face, always turned toward home. The moon watches over Earth with that same still face. But Earth is not the only world with tides. Across the solar system, gravity pulls at moons and planets in ways that are sometimes gentle, sometimes violent, and sometimes so extreme that they reshape entire worlds from the inside out. Consider Jupiter. It is the largest planet in our solar system, more than 1,000 times the size of Earth. Its gravity is immense, and it has moons. One of those moons is called Io, and Io is the most volcanically active world we have ever found. Its surface is covered in erupting volcanoes, rivers of molten rock, and plains of sulfur that glow yellow and orange and red. Scientists once expected a cold, quiet, dead rock. What they found was something burning. The reason is tidal force. Jupiter's gravity pulls on Io with tremendous strength, but two other large moons, Europa and Ganymede, also pull on Io from different directions as they orbit. These competing pulls stretch and squeeze Io the way your hands might knead a ball of dough. This squeezing happens over and over, millions of times across millions of years. The friction from all that squeezing generates heat deep inside Io's rock. That heat has nowhere to go but up. And so Io erupts, constantly, endlessly, driven not by radioactive decay or leftover heat from its formation, but by tides, by the simple, relentless pull of gravity. Europa tells a different story. Europa is also a moon of Jupiter, slightly smaller than our own moon, and its surface is a sheet of ice, smooth, pale, cracked with long lines that look like the surface of a cracked eggshell. Beneath that ice, scientists believe there is a liquid ocean, a global ocean wrapped around the entire moon, kept liquid by the same tidal heating that sets Io on fire. Europa's tides are gentler. The heat they generate is enough to melt ice, not rock. And that liquid water, hidden beneath miles of frozen surface, is one of the most exciting places in the solar system. Where there is liquid water and heat, life sometimes finds a way. Europa has both. This is what makes tidal force so remarkable. It does not just move water on a beach. It can melt ice on a moon 400 million miles from the sun. It can drive volcanic eruptions on a world with no atmosphere. It can create the conditions for liquid oceans in places where sunlight never reaches. Tidal energy is not a small thing. It is one of the great engines of the solar system. Now think about Earth. Our moon is large for a planet of our size. Most rocky planets either have no moons or very small ones. Mars has 2 tiny moons, each one shaped like a lumpy potato, each one only a few miles across. They pull almost no tide at all. Venus has no moon. Mercury has no moon. Earth is unusual. Our moon is big, and it is close, and it has been with us for billions of years. That size and closeness gives Earth tides that are strong enough to matter, strong enough to slow our rotation over time, strong enough to stabilize our axial tilt, the angle at which Earth leans as it orbits the sun. Without the moon's steadying pull, scientists believe Earth's tilt could wobble dramatically over millions of years. A wildly changing tilt would mean wildly changing seasons. Ice ages that came and went without pattern. Climates that swung between extremes too fast for life to adapt. The moon holds us steady. It keeps our tilt within a narrow range. It gives our seasons their rhythm and their predictability. That predictability matters more than it might seem. Life on Earth evolved inside those steady rhythms. Plants grew toward a reliable sun. Animals built their cycles around seasons that repeated in the same way, year after year. The tides themselves became a clock for coastal life, a signal for spawning, a schedule for feeding. All of that depends on a moon that is the right size, at the right distance, doing its quiet work. Change one thing and the whole system shifts. Make the moon smaller and the tides weaken, the tilt wobbles, the seasons lose their shape. Move the moon farther away, and the same thing happens slowly over millions of years. The moon is already drifting outward, as we have seen. One day, far in the future, it will be too far to hold us quite so steady. But that day is not today. Today the moon is close. Today the tides are strong. Today the balance holds. And in that balance, quietly, the living world goes on. Long before any of this was as it is now, Earth was a very different place. The moon was closer. The days were shorter. The tides were enormous. And the story of how we know this is itself a quiet kind of wonder. Scientists can read ancient tides the way you might read old letters. The clues are written in rock. Certain layered stones, called tidal rhythmites, preserve the rise and fall of tides from hundreds of millions of years ago. Each thin layer in the rock marks one tidal cycle. Count the layers, and you can count the tides. Count the tides, and you can measure time itself, reaching back into an earth that no living thing remembers. One famous set of these rocks was found in South Australia. Scientists believe they are about 620 million years old. The layers inside them suggest that back then, a day on Earth lasted only about 21 hours. The moon was closer to our planet, and Earth was spinning faster. The tides that washed those ancient shores were far taller and far more powerful than anything we see today. The ocean was a wilder place. But here is where the mystery deepens. We have only found a small number of these ancient tidal records. The rock layers that preserve them are rare. Most of Earth's old seafloor has been pulled back down into the mantle. That thick layer of hot rock beneath the crust, and melted away. The record is incomplete. Scientists piece together what they can, but enormous stretches of tidal history are simply gone. The ocean kept no permanent diary. This means there are long chapters of Earth's past that we cannot yet read. We know the broad shape of the story. The moon was closer. The tides were stronger. The days were shorter. But the fine details remain out of reach. Exactly how tall were the tides 1 billion years ago? Exactly how fast was Earth spinning 400 million years ago? These numbers are still being worked out carefully from whatever thin slices of ancient rock have survived. There is another open question that scientists find deeply interesting. Life first appeared in the ocean, and the tidal zone, that strip of shore that floods and drains with each tide, may have played a role in how life became complex. The tidal zone is a place of constant change. It is wet, then dry, warm, then cool, exposed to sunlight, then covered in water. Some researchers suggest that this rhythm of stress and relief may have pushed early life to adapt in new ways. The tides may have been a kind of teacher, but we do not yet know how strong that connection truly is. We do not know which tidal conditions were best for early life. We do not know whether life would have taken the same path on a world with weaker tides, or stronger ones, or no tides at all. These are questions that sit at the edge of what science can currently answer. They are not frustrating questions. They are invitations. There is also the question of the deep past, before complex life existed at all. For most of Earth's history, the planet was home only to single-celled organisms. That period lasted more than 3 billion years. During all that time, the tides were rising and falling. The moon was slowly drifting outward, and the days were slowly growing longer. How did those changing tides shape the chemistry of the early ocean? How did they mix nutrients and heat and minerals across those ancient shallow seas? Scientists are still building the tools to answer these questions. Even the tidal rhythmites themselves hold unsolved puzzles. Different rock formations from similar time periods sometimes give slightly different answers about the length of the ancient day. The numbers do not always agree perfectly. This could mean the rocks formed in slightly different conditions. It could mean the tidal patterns were more complex than a simple count suggests. Sorting out these small disagreements is careful, patient work, and it is still ongoing. What is clear is that the tides have been part of Earth's story from nearly the very beginning. They have shaped the shore, mixed the sea, and kept time in stone. They carried energy from the moon down into the ocean, and from the ocean into the rock. And in those rocks, if we look carefully enough, the old tides are still there, quiet, patient, waiting to be understood. There is still so much left to find, and that is not a gap in our knowledge. That is a door left open with something wonderful on the other side. Long before anyone wrote down the rules of the sea, sailors already knew them. They learned by watching, by waiting, by losing ships and trying again. The knowledge of tides was not born in a library. It was born on the water in the dark, with the wind coming in and the current pulling hard beneath the hull. The earliest seafarers noticed patterns quickly. The water rose and fell on a rhythm. It came in, it went out, and it did so again. They did not know about the moon's gravity. They did not have equations, but they had eyes and memory, and that was enough to begin. Ancient Polynesian navigators were among the most skilled tide readers the world has ever known. They crossed thousands of miles of open ocean without instruments. They used the stars, yes, but also the feel of swells beneath their canoes. They read the way currents shifted near islands. They noticed how tidal flows changed as land approached. This knowledge passed from elder to child, spoken aloud. memorized like a song. It kept whole civilizations connected across the vast Pacific. In the Mediterranean, Greek and Roman sailors kept careful records of how tides behaved in different ports. The Mediterranean Sea itself has very small tides, often less than a foot. But sailors who ventured out through the Strait of Gibraltar into the Atlantic found something startling. The tides there were enormous by comparison. The Greek explorer Pytheas, sailing north around 325 BCE, described tides so large that people who had never left the Mediterranean could barely believe his accounts. He was telling the truth. Arab navigators in the Indian Ocean developed some of the earliest written tide tables. They tracked the moon's phases and matched them to the rise and fall of water in the harbors they used. They knew that a full moon and a new moon brought the strongest tides. They knew that timing a departure wrong could strand a ship on a sandbar for hours. Their tables were practical tools built from generations of careful watching. In medieval Europe, monks in coastal monasteries kept tide records for practical reasons. The sea controlled when boats could leave, when fish could be caught, when pilgrims could cross the tidal flats to reach sacred islands. The famous Mont Saint-Michel in France sits on a rocky island that becomes surrounded by water at high tide and accessible by land at low tide. The tides there move fast and far. Knowing their schedule was not just useful. It was a matter of life and death. The English port of London sits far up the Thames River, and tides reach all the way there. For centuries, the timing of the tide determined when ships could move in and out of the port. Harbor masters kept records. Merchants planned around them. The rhythm of commerce in one of the world's great cities was quietly set by the moon. Isaac Newton gave the world the first real mathematical explanation of tides in 1687. His theory of gravity showed that the moon's pull on the ocean was the engine behind the rise and fall. For the first time, the ancient pattern had a physical cause that could be written down and calculated. But Newton's model, while groundbreaking, was not perfect. The real ocean is complicated. It has basins and continents and shallow shelves that all change how tides behave. It was Pierre-Simon Laplace, a French mathematician working in the late 1700s, who built a more complete theory. He treated the ocean as a fluid moving across a spinning planet and worked out equations that could account for much of the complexity. His work became the foundation for modern tidal science. By the 1800s, tide predicting machines had been built. These were mechanical devices, full of gears and wheels that could calculate the expected tide for any port on any future date. Lord Kelvin, the Scottish physicist, helped design some of the most sophisticated ones. A machine could turn a crank and print out a year's worth of tidal predictions for a harbor. Sailors finally had something they could trust completely. Today, tidal predictions are made by computers, drawing on centuries of recorded data and the mathematics that Laplace and others built. The predictions are accurate to within minutes. Ships move through busy ports with confidence. Coastal engineers plan sea walls and bridges around tidal ranges. Scientists track long-term changes in sea level against the background of the tide's steady pulse. All of that knowledge traces back to someone standing on a shore a very long time ago, watching the water rise, watching it fall, and deciding to remember what they saw. The sea was the teacher, and people, patient and curious, were very good students. People learned to read the tide. Then, slowly, they began to wonder if they could use it. The tide is not just a pattern to observe. It carries enormous energy. Every time the ocean rises and falls, it moves billions of tons of water. That movement is a force, and for centuries, people have tried to put that force to work. The earliest tidal mills appeared in Europe more than 1,000 years ago. A tidal mill worked by trapping water behind a small dam at high tide. When the tide fell, the trapped water was released through a narrow channel. The rushing water turned a wheel. The wheel ground grain into flour. It was simple. It was elegant. The moon was doing the work, and the miller was just paying attention. These mills dotted the coastlines of Ireland, England, and France through the Middle Ages. Some of them operated for hundreds of years. A few ruins still stand today, their stones worn smooth by salt air quiet reminders that this idea, using the tide to power human life, is not new at all, but the modern version of that ancient idea is far larger. Today, engineers build structures called tidal barrages. A barrage is a kind of dam built across the mouth of a river or bay where tides are strong. As the tide rises, water flows through tunnels in the barrage and spins large turbines. As the tide falls, the water flows back through, spinning the turbines again. The turning turbines generate electricity. The tide comes in, power flows. The tide goes out, power flows again. Twice a day, every day, without fail. The La Rance tidal barrage in France was completed in 1966. It stretches across the mouth of the Rance River in Brittany, a region with some of the strongest tides in Europe. For decades, it was the largest tidal power station in the world. It still produces electricity today, quietly and steadily, powered by nothing more than the moon's pull on the sea. The Sihwa Lake Tidal Power Station in South Korea surpassed it in 2011. It now holds the record for the world's largest tidal power facility. It generates enough electricity each year to power roughly 500,000 homes. The moon rises, the tide pushes in, and the lights stay on. These are not small achievements. They point towards something important. The tide is a renewable source of energy. It does not burn anything. It produces no smoke. It does not depend on the wind blowing or the sun shining. It depends only on gravity, and gravity never stops. As long as the moon orbits the earth, the tide will rise and fall. Scientists estimate the moon will remain close enough to drive meaningful tides for billions of years. There are newer ideas too. Engineers have designed underwater turbines that sit on the seafloor in places where tidal currents run fast and strong. These turbines look something like wind turbines, but instead of catching air, they catch moving water. The water is far denser than air, which means even a slow current carries a great deal of energy. Tidal stream generators, as they are called, have been tested off the coasts of Scotland, Canada, and Australia. Some are already feeding power into local grids. The potential is real. Scientists have calculated that tidal energy could could supply a meaningful share of the electricity needs for coastal nations. The ocean is vast. The currents are strong, and the moon is not going anywhere. There is something worth sitting with here, the same force that pulled the seas of ancient earth, that carved the bay of Fundy, that guided the canoes of Pacific navigators, that filled the salt marshes, where the first complex life learned to breathe air. That same force is now spinning turbines and lighting cities. The moon has been shaping life on this planet since before there was anything we would recognize as life. And it is still shaping us, still offering something, still quietly at work. The atoms in the ocean were forged in the hearts of stars long dead. The moon itself was born from a collision so violent it reshaped the young earth. Out of that ancient chaos came the tides. Out of the tides came the rhythms that life learned to follow. Out of those rhythms came the curiosity that led people to watch the water, measure it, understand it, and finally, gently, learn to use it. The moon pulls, the sea answers, and somewhere on a coastline right now, a turbine is turning in the dark, and the lights are on, and the tide is still coming in. And so we come to the end of this long, quiet night of learning. The moon is still up there. Right now, as you rest, it hangs in the dark above a turning world. Its pale light falls on open water. It falls on rocky shores where waves pull back and then return. It falls on tide pools full of small, still creatures waiting for the sea to come home. The moon has been doing this for about 4.5 billion years. That number is almost impossible to hold in your mind. But the pull has never stopped. Not once. Through ice ages and warm ages, through the rise and fall of every species that has ever lived on this planet, the moon has been there, and the tides have answered. Think about what that means for life. The earliest living things on Earth were single cells drifting in shallow water. They had no eyes, no brains, no sense of time, but the tides moved around them. The water rose and fell. Nutrients washed in and out. Over millions of years, life began to track that rhythm. It became part of the code inside living things. Scientists have found that even today, many creatures carry internal clocks tuned to the tidal cycle. rhythm of the moon is written into their biology and into ours too, in quiet ways. The human body is mostly water. Our earliest ancestors crawled out of tidal zones. Some researchers believe the rich, changing environment of the intertidal zone, that strip of shore between high and low tide, may have pushed early life toward greater complexity. The tides did not just shape the coastlines. They may have helped shape us. The ocean covers about 71% of Earth's surface. It holds about 97% of all the water on the planet. And every drop of it, every single drop, is touched by the moon's pull. The tides move through the deep ocean as long, slow waves, barely noticeable on the open sea, but building into something powerful as they approach the shore. The energy in a single tidal wave crossing the Pacific is almost beyond measuring. And yet the moon does all of this without touching the water at all. It never comes close. It sits an average of about 239,000 miles away. And from that distance, its gravity reaches down through space and lifts the sea. Gently, steadily, without fail. There is something deeply calming about that. The universe runs on forces we cannot see. Gravity is invisible. We only know it by what it does. And what it does, in the case of the moon and the sea, is create one of the most reliable rhythms on Earth. The tides have never missed a cycle. They have never forgotten to come in. They have never failed to go back out. Right now, somewhere on this planet, the tide is rising. Water is climbing a rocky cliff face, filling a cave, lifting a small boat at its mooring. Somewhere else, the tide is falling. A wide mudflat is appearing, brown and gleaming, and a heron is already walking out across it, looking for fish. These two things are happening at the same time, on opposite sides of the world, because the ocean is one connected body, and the moon pulls it all at once. The moon itself is quiet and still. It has no weather, no wind, no ocean of its own. Its surface is covered in fine gray dust that has not moved in millions of years. Footprints left by astronauts in 1969 are still there, perfectly preserved. The moon just watches. It turns its same face toward us always, locked in that slow, faithful orbit, and it pulls. And the sea always answered. It answered before there were eyes to watch it. It answered before there were words to describe it. It will answer long after we are gone, long after every city and every ship and every tide chart ever made has turned to dust. The moon will still be there. The sea will still rise. The rhythm will go on. You are part of that rhythm. Your body, your atoms, your ancient biology. You are made of the same stuff as the ocean, shaped by the same forces, tuned to the same turning world. The moon is pulling the sea right now, and the sea is breathing in the dark. And somewhere a wave is folding softly onto a quiet shore. Rest now. The tides will keep. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.